Hi everyone, we're FineMotion team and here we present our approach to the GENEA Challenge 2023. As in previous challenges, the task of this challenge is to generate conversational gestures from the agent speech. The main difference from previous challenges is that proposed systems should also take into account the interlocutor's behavior. Previous year we tried sequence-to-sequence and autoregressive approaches, but they were convergent to the rest pose because the amount of idle motion in the dataset. To overcome this problem, we tried some teacher forcing techniques, but the results are still far from natural motion.
Now she's like back again, like she's like my all the videos, like she's just smiling around like when take her out. Yeah.
So, in the current challenge we decided to find a solution from other tasks. Very similar approaches are used to create character controllers in video games. The main requirements for such models are stability of motion and responsiveness for user input. So, this is exactly what we need. The most of successful character controllers are built upon mixture of expert frameworks and works in autoregressive manner. And the quintessence of these approaches, in our opinion, becomes DeepPhase, a periodic autoencoder which extracts periodic features in lower dimension than original motion. Then these features are used as gating input in mixture of experts to force generated motion to be stable, periodic, and as a result more realistic. So we decided to build our approach on a mixture of expert framework with DeepPhase features as gating input. To use a large amount of control features, we also decided to use additional recurrent encoder instead of the control vector. So let's go through our approach step by step. First, we need to train periodic autoencoder. The VQ-VAE architecture utilizes a temporal convolutional autoencoder, additionally applying real fast Fourier transform to each channel of the latent space. To prepare input for VQ-VAE, we first extract positions for 26 joints, and then calculate velocities and smooth them via Butterworth filter. Here you could see curves for root joint position, velocities and smoothed velocities. There is a training configuration. The obtained model extracts amplitudes, frequencies, offsets and phase shifts from each time window. The result phase manifold is calculated from amplitudes and phase shifts in the following way. Then we calculate the resulting feature tensor by sliding the input window. Here you can see obtained phase features separated by latent channels for a 10-second sample. We also try to train VQ-VAE on joint rotation angles, but resulting features don't look like periodic functions. As mentioned before, our generator model is built upon a mixture of expert framework, which consists of two main blocks. First is a gating network, which takes extracted phase features and returns weights distribution over experts. The second block is a motion prediction network, which utilizes these weights to make a linear combination of linear layers and predicts the final output vector. The inputs of motion prediction network are character state on current frame, which contains joint velocities and rotations, and control vector, which is extracted via additional recurrent control variables encoder from a window of control features. To drive our motion prediction network, we extract audio and text features from agent speech, which are male frequency capture coefficients and glove embeddings, respectively. Text features we align with audio by token spans. In addition to agent speech features, we also use interlocutor's motion encoding via VQ-VAE. For that, we split motion data by audio bits and transform obtained samples with codebook encoding. Then we also align transformed vectors as we did it with text embeddings. Finally, our generator is trained to predict character state on the next frames, as well as future absolute values of phase features and its displacements, which are used to blend phase values. The generator is trained in end-to-end manner for each frame independently, so we didn't use teacher forcing techniques as before. Here you can see an example of generated motion.
To do those,
Yeah, I felt like similar thing. Like my although he's also, I think he's kind of like flexible in findings, but he also like guiding you towards some specific topic. Because I think one risk we want to avoid is like, because you have this freedom, you might explore so many different things.
Yeah.
You won't converge,
yeah,
and
totally.
you need to have someone to push you towards some direction that you start to really dive deep.
During human evaluation, our model has shown good results by human likeness and appropriateness for interlocutor's motion, but poor results by appropriateness for agent speech. We attribute this to the relatively poor agent speech features and dependence of gated network outputs mostly from phase features. Here an illustration of predicted weights distribution through the time along with speech features. In conclusion, we want to emphasize that mixture of expert model with DeepPhase embeddings has shown a significant improvement in stability of motion from our previous approach. It also remains relatively simple and can be used in real-time applications. Thank you for your attention and have a nice day.